Hello everyone, welcome to the GeoEcologist. I am Dr. Krishnanand and you have been watching my videos on various topics of geography, environment and research methodology on my channel, The GeoEcologist. If you are new to this channel, consider subscribing, and also for the earlier videos, you can go to our playlist section. Now in this ongoing series on hydrology, today we are going to learn the basic concepts of river basin, where we'll be discussing morphometric analysis, we'll be talking about river profile, we'll be also looking into river dynamics. So if you want to learn all these concepts, watch the video till the end. It's going to be really interesting and we are going to do it from scratch to the advanced level gradually. So now let's learn. But before that, let me remind you, please do share these videos with more and more people. And also, if you really want to support us, please join this channel. So now let's learn. So in hydrology, today's video is going to be about river basin. The basic concepts we're going to talk about. Also, we'll be looking into morphometry of river basins, channel profiles, we'll be looking into fluid dynamics, and also some characteristics of alluvial channels. So now, one by one, let's understand. So the first question is, what is a river basin? So if you observe here, what is a drainage basin? This is particular area where you have a main river and its tributary. So this entire area is called a river basin. So area drained by a river and all of its tributary. So river basin is made up of many different watersheds. Now, if you observe, this tributary will have certain more tributaries. So this is one watershed, this is another watershed, this is another watershed. So if you observe, these are different watersheds, and as a whole, you can also call it a watershed as well, right? So right from headwaters to the estuary, or you say mouth of the river, this all area is a watershed. So watershed is basically what? It's a small version of a river basin. So the concept of scale comes to the picture here when we talk about it. Now, let's look into one more important thing, that every stream and tributary has its own watershed. That's what we talk about. So this could be one watershed, this could be another watershed. So multiple watersheds as well as one big watershed. So this is something where you observe it's a systems approach in hydrology that we operate here. Now, these streams, ponds, wetlands, lakes, all of them are part of a river basin itself, right? So now let's understand with one example from US. So Mississippi River, the most famous river, and it has a bird's foot delta out here, if you remember. So how many river you see here joining it as a tributary? So you have Missouri here, right? Upper Mississippi is here, Ohio is here, Tennessee is here, then you have Arkansas and Red and White River, and here is Lower Mississippi. So can you observe what's there? These are all 6 major watersheds. And if I say as a big river basin, this is one river basin of Mississippi, and these are small watersheds, right? Or you can say this is the entire, at a large scale, a Mississippi watershed in total as well. So the scale concept, and remember, this is one example. In South Asia, when we say we have Indus, Ganga, and Brahmaputra, right, as major ones. And apart from this, you have so many other examples you can observe. Now, let's understand few important terminologies and people. So let's recognize people like Stanley Shum. If you remember him, we have talked about his model in geomorphology lecture, episodic erosion model, where you have landforms development. So Shum talked about a very interesting thing, that the entire fluvial system can be subdivided into 3 zones. The first zone is zone of production, from where these consequent streams rise, right? This is the production zone. Then you have zone of transfer, right? So this particular zone where sediment gets transferred from zone 1 to the zone 2. And then you have the third zone where you have zone of deposition. So this zonation of the entire river basin was done by Shum. That is important to remember. Now, let's talk about another great scholar from US, and his name is Robert Elmer Horton, R.E. Horton. So remember this person, he's also regarded as father of modern American hydrology, and he was an American hydrologist, geomorphologist, a civil engineer, a great scientist, and there are medals in the name of this Horton. So remember, what did he do? very important things in hydrology that you studied in earlier lectures are contributed by his studies of New York streams. So Horton determined the degree to which rainfall could reach the aquifer and how this is recharged. So recharging the aquifer concept, infiltration capacity concept, and also the structure of hydrology that we studied through systematic approach of infiltration, evaporation, interception, transpiration, and overland flow. This was all given for the first time, analyzed and separated by Horton himself, right? So Horton was the first person to demarcate and label, which you are familiar now, the stages of water cycle, right? So that's his contribution. But furthermore, in morphometry of river basin, he defined R.E. Horton, remember the name, and also the Strahler, right? When he modified. So Horton was the first person in 1945 who defined the measurement of shape of a particular drainage basin, right? This is called morphometry. So morpho is for shape and metry is for measurement. How do you measure the shape, right? So main purpose of this work was to discover holistic stream properties from the measurement of various stream attributes. And here he made a very interesting ordering classification system, that is hierarchy of a stream, where you see first order stream, second order stream, third order stream. So what is important here? Let's read it. Once the first point is that in this system, channel segments were ordered numerically, so numbers were given from a stream's headwater to a point somewhere down the stream. So we'll start with headwater. The first stream is called number 1, right? And then as this number 1 joins together, it forms number 2. So joining 1 and 1, it will become 2. And then again another 1, it will be falling into 2 and further 1. So here it becomes number 3 when 2 and 2 meet. Right? So this is important here. When 2 and 2 is meeting, it's becoming 3, right? So this is how we look into it. So numerical ordering begins with tributaries at the stream's headwaters, assigning value 1, and joining of 2 first order is 2, and joining of 2 second order is 3. This is how. So 1 and 1, right? It becomes 2. Then 2 and 2, it becomes 3, and so on. So this is called Horton's formula. Remember this. Now, for example, the ratio between the number of stream segments in one order and the next order is called bifurcation ratio. Remember this, how a stream is bifurcated. Now, why do you require bifurcation ratio? It talks about how well distributed or branched is your river basin. How many tributaries are there, at what distance, and what is the shape. So remember, when we did that lecture in drainage basin and its various types, this was based on bifurcation ratio. So remember, this is a very important scientific word, and look at the calculation here given by Horton. So here law of stream numbers is given. So first order streams, if you calculate, it's 10. Second order streams, it's 3. And third order stream, it's just 1. So this is number of segments. And what is bifurcation ratio? It's this. So how do you calculate the bifurcation ratio? It's very simple. If you observe, this is first and this is the second. So when you divide, you get 3.33. Then further, so if you divide this, so you get 3 value, right? So this is something that you talk about. It's the ratio between number of stream in the one order and the next order. So if you calculate this ratio, you will get this particular bifurcation ratio. And this is what we call as law of stream numbers. And then Horton further applied this morphometric analysis to a variety of streams and attributed a lot of work that we say as laws of drainage composition. So who gave us the laws of drainage composition? Horton's work. Now look at this particular flow diagram and you'll understand that Hortonian overland flow, here is the word. Remember this. So this Hortonian overland flow has been talked about here, which you observe here, right? Number 1. Right? So this is something which is important. We have talked about through flow, groundwater flow, saturation over land flow. So these are the important things. Now, Horton's law of stream length, if you observe, suggested that a geometric relationship existed between number of stream segments in successive stream order. So this is something which is important. It's not arithmetic, it's geometric. Right? So this is important to know. And law of basin areas indicated that mean basin area of successive order streams formed a linear relationship when they put on the graph. So these kind of relationships was established by Horton. Now, let's understand what is drainage density and how will you compute. So in addition to mathematical relationships found in stream ordering through Horton's formula, and further, you observe that there is a relationship called drainage density. You can calculate drainage density. How will you do it? So drainage density is a measure of length of a stream channel per unit area of drainage basin. right? So mathematically, what is it? Stream length by basin area, right? If you have these two data, you can calculate drainage density, right? So the measurement of drainage density provides a hydrologist or a geomorphologist with very meaningful, useful numerical measure of a landscape dissection and runoff potential. Remember this, landscape dissection and runoff potential. If you want to know, you need to know what is the density of drainage in that area, right? So closer investigations and the processes responsible for this density, you will understand the factors here. So which are the factors? Climate, topography, soil infiltration capacity, vegetation, geology. All these factors are these factors that influence the or control the drainage density, right? So now let's look into the profile of a river. I'm sure you have heard of long profile of a river, longitudinal profile of a river, right? Cross profile of a river. So what exactly is it? Look into this. So if this is the source of the river and this is mouth of the river, so along its flow direction from source to mouth, this is called what? A long profile. And when, if you observe long profile of a river, if the river is originating in the top of the hill, so gradually you will see that there is a change of the levels, right? So if you have a sudden change in the level, this point is called nick point, right? So you have a waterfall most of the times at nick point. So it's called a nick point waterfall. If you remember, we have a very famous area in India at Madhya Pradesh. And what is that area? We have Bheda Ghat. And what is the waterfall name? Okay, let me not tell you. Can you comment in the comment section about what waterfall is there? And it's a Nick Point Fall, right? So if you don't know, just Google it, Bheda Ghat, Nick Point Fall, and just comment what is the name of that waterfall in the longitudinal profile of which river. If you see, the river name is Narmada River, right? So this is something which is interesting. Now, this is a longitudinal profile where river's gradient changes, as you see here. And what is a gradient? The degree of slope, right? So the degree of slope changes as the river goes further, right? So now what you observe further, through the long profile of a river, what happens from erosion to deposition, right? And here is a center point here from where erosion and deposition changes the ratio. This is called the profile of equilibrium, right? So if this kind of profile is available where you don't see any nick points here, right? So this particular kind of profile where you don't see a nick point, it's just a smooth profile, means whatever material is eroded here is exactly deposited here. Nothing is left here, right? So this kind of profile of a river is called graded profile of a river, right? So if a river is graded, means what? The profile is this smooth, right? So with this particular long profile, what you study is the grading. So the idea is, it's an ideal scenario. Every river in its lifetime, right, wants to become graded ultimately. So all the nick points would be eliminated, right, or eroded. This is very important concept, right? So grading of a river. Now, if you observe cross profiles of a river, and cross profiles of a river gives us an idea about all these concepts that we have talked. So if this kind of channel is available, do you see the features where faulting is involved or a rift valley is involved? So this will tell you about how exactly is the river profile and the area or the landscape. So river cross profiles show us cross section of a river and valley at certain points, and it also helps us to understand how river changes as it moves from upper to lower course, and also the processes. So look here, this is narrow channel, then in floodplain it became a wide channel, right? And further wider, what flood plain and the valley structure that you observe here. So this is how river is actually lowering down, and also what is happening from vertical erosion, it's going to lateral erosion, right? This is how we study cross profile, right? So now let's look into further more concept, channel velocity. Now, what is the importance of velocity here? Velocity is along the profile, what is the speed in a given direction, right? The kinetic energy is important here of a river. So lowest velocities in the river, where will you find? In the shallow water zone, right? So friction is greatest here. But maximum velocity in a river, you'll find where channel is deep. So deepest track of a river, if you observe, is called a channel thalweg. The word is thalweg. Remember this, right? Now let's observe some things from fluid dynamics. And what do you see? Channel discharge capacity. How much is the transportation capacity, or how much is the discharge and maximum discharge that any channel can support transport is called canal capacity. So if you have created a canal and you want to measure, you can measure a discharge. So there is something called hydrograph which is used for this, right? So observe here, stream discharge or channel discharge is the volume of water passing through a particular cross section. If this is a stream and we take this cross section, so from here, right, what is that amount of or volume of water that passes per unit time, right? So cubic meters per second or cubic feet per second, you can calculate from here. And remember, one more thing here is given, this base flow. So discharge of perennial flowing stream is provided by influx of groundwater into the channel, and this influx provides what is called as basal flow. So basal flow, right, is something where on the base every time there is a flow. At flood season there is upward, but at base there is always a flow. Now, how will you compute? What is the formula? So discharge is Q value, and which is equal to W into D into V. So what is W? It's channel width, D is average channel depth, and V is average velocity, right? So this is how you can compute with the data. Now, what is stream energy? So it's the kinetic energy that we talk with the velocity. So stream's capacity to erode and transport sediment is regulated through the energy. If energetic is the stream, it will have more capacity to erode as well as transport the sediment, isn't it? And sedimentary load capacity, it's exactly what? How much sediments can the stream carry through the long profile of the river, right? So stream load is broken into three types: dissolved, suspended, and bed. So dissolved is what material is dissolved in the water and it's getting transported. Suspension, where material is floating alongside, and bed load is the deposition where material is on the bed and also moving ahead, right? These are three types of sedimentary load capacity. Now, what is transportation capacity? The volume of load, remember this, which can be carried by the stream, and this is called transportation capacity of stream water under a particular condition. Now at the end, let's observe some famous alluvial channel patterns and some important terminologies. Now there is a very common thing that anything that looks like this, we call it, it's a meandering system or meander river. But technically, there are different things that we should look into. So alluvial channel have two main properties. One is sedimentary load and there is sinuosity. So what is this sinuosity? A ratio between stream length to valley length. So if you observe, this is the straight line distance, which is straight line, and here is the actual channel stream channel length. And so length of stream channel by length of straight line, this is called sinuosity, this ratio. And remember Horton's work, erosional development of streams and their drainage basins, Geological Society of America, 1945. This is where it was discussed. So what you need to know, sinuosity, and on the basis of this ratio, you can say a channel is straight, or is it sinuous, or is it meandering? Not every channel that moves like this is meandering, right? Technically. So, according to Leopold and Woolman, 1957, river channels are divided into straight channel, sinuous channel, meandering channel. And look at this, sinuosity index less than 1.05 is straight, right? Roughly a straightish channel. Then sinuosity index between 1.05 to 1.5 is sinuous channel, and meandering is more than 1.5. So the ratio has to be 1.5 or above, right? Now, let's observe this Morisawa's, Shum's, and Mayal's work, and this is taken from Professor Savindra Singh's work in his book. It's mentioned, so you can read it from there as well. Type, so straight channel, sinuous channel, meandering channel, braided channel, anastomosing channel. And look into the sinuosity indexes here so that you'll observe, right? This is very clearly given, and what is the erosive behavior, what is the sediment load type, this you can observe directly from here, right? How it looks like. Now, ana-branching channel is something which is the last thing that we discuss. And ana-branching channel is what? The flow of the main stream is divided into two or more separate channels, and relatively rare in comparison to braided and meandering channels. So what you observe, the branches here, okay, these branches are ana branches. So here is a tributary stream, and one main stream is divided into multiple. So here is the trunk stream, and here is the small ana branches, and further they go to the mouth. So here typically this is cut into floodplain divided into large islands. So in between, you will see a lot of riverine islands. And the famous island, Majuli, is there in Brahmaputra. You know this. So you have many Anna branches available there. So this is the concept that we need to understand. So now I hope that you understood these basic concepts and you had a good revision. And in the sessions to come, we'll be talking more on other topics of hydrology. So stay tuned, and all the best wishes to all the learners. Please do subscribe to our channel, do join our channel to support us, and please do share these videos amongst your people, amongst your circles, right? So that we have greater outreach. Best wishes.